Hello everyone, it's Andrea here, a PhD student from the University of Exeter, and today I'm gonna talk about recurrent neural networks, and specifically on the interpretability problem of recurrent neural networks, which is my PhD research topic. That's the outline of my speech. I'm going to provide a mild introduction on recurrent neural networks. I will briefly explain the black box problem of recurrent neural networks. Then I'll talk about non-autonomous dynamical systems and about the echo state property in the non-autonomous dynamical systems setting. And then I'll talk about some of the new results that I found along my PhD. So first of all, I want to make clear the difference between feedforward and recurrent neural networks. Recurrent neural networks are dynamical systems inspired to some extent by the brain, and here in the picture you can see a schematization of a feedforward neural network. Black dots are supposed to be the neurons of the network, which are usually real numbers, and we start with a input vector labeled as u at time k, and that's a two-dimensional vector, and we pass the input vector through this matrix Win, and then we non-linearly transform the result by means of this nonlinear function phi called the activation function, which is usually a continuously differentiable, bounded, and monotonically increasing function. You can think to the hyperbolic tangent as an example of activation function. So we get the resulting vector here, and then analogously we apply this matrix and again the activation function, and we get another vector, and so on and so forth until we reach the last hidden layer, and then we compute the actual output of the neural network as through this map G and this matrix WO. So as you can see, the information flows forward in this particular architecture, and that's why it's called feedforward neural network. And at the end of the game, it's just a from the mathematical point of view, it's just a nonlinear function which maps input from the input space to the output space. Of course, it can be an extremely complicated and complex function, since it will be a composition of many nonlinear functions, as you can see here for this particular example, and there are many parameters, which are all the entries of these matrices here. But as I said, mathematically it's just a nonlinear function. But what if we add a recurrent connection from the last hidden layer to the first hidden layer? And that can be done by means of this additional matrix WR representing the recurrent connections. And in this particular case, we can view the vector x as the internal state of the neural network, and adding a recurrent connection makes a feedforward neural network a recurrent neural network, which is from the mathematical point of view a dynamical system. And we can see as this vector x the internal state of the network, which is evolving as time goes ahead. And so the internal state x at time k would depend on the internal state at the previous time k minus 1 and the current input vector u, and that can be expressed by this map that I labeled as G. Of course, this loop makes recurrent neural networks suitable to deal with temporal data, and it is exploited to solve tasks as speech recognition, handwriting recognition, and so on. So in order to move on, why not to simplify the architecture of the recurrent neural network, considering just one hidden layer, but very large. Then that's called the reservoir, and here you can see an example of a reservoir computing machine. The reservoir is represented by this gray region. The black dots are the neurons of the network. All these arrows inside the gray region are supposed to be the recurring connections of the neural network, and as before we've got the input signal u at time k, which is injected into the network by means of this matrix win. We read out the internal state of the network by means of this matrix wo, and we get the output vector z at time k, and also we allow to feedback the output into the network by means of this additional matrix wfp, which can be useful in some tasks. And so that's the basic equation of a reservoir computing machine without leak rate. And the output vector z, it is computed as a function of the internal state x at time k, and we call this function psi, which can be, as in the picture, a linear function, as you can see, by means of this matrix wo, or more generally by a nonlinear function psi. It really depends on the task. So summarizing, a recurrent neural network is a input-driven system, is a non-autonomous, non-linear, high-dimensional discrete-time dynamical system, which is the nightmare of all mathematicians, since it is really hard to understand the behavior of these dynamical systems. Here in this equation we can see also there is the parameter alpha, which is called the leakage rate, which basically tunes the timescale of the recurrent neural network. So it is a non-autonomous dynamical system, which is because of the presence of the input signal u, which at each time step changes the equation ruling the dynamics. And it is nonlinear because of the presence of these two functions, phi and psi, the activation function and the readout function. And it is usually very high dimensional, since there can be thousands or even millions or billions of dimensions. So these matrices here will usually be very, very large, as well as this vector x. So I will make some assumptions on this dynamical system, specifically that the readout function psi is a continuously differentiable function. I will assume that the activation function phi is a continuously differentiable function as well, which is bounded between two values minus L and plus L. I will assume that it is, as usual, a monotonically increasing function, and that the first derivative of the activation function has a unique maximum point in 0. Just think about the hyperbolic tangent to have something fixed in mind. I will also assume that the phase space where the internal state of the system is evolving is a compact space of real values, and also that the input values are taken in a compact space of real values. And there will be also a technical assumption on the map G, such that for all input values U, this map is a local diffeomorphism onto its image. Now I want to spend a few words on training, and specifically on what is meant by training a recurrent neural network. All the training procedures of recurrent neural networks are basically sharing the same idea, which is to find and tune all the parameters of the model, which in our case are all these, the entries of these matrices, the function psi and the parameter alpha, and we want to tune those parameters in order to get a suitable configuration of parameters in order to solve a specific task. So this is achieved by means of a definition of a loss function, which will be a function of all the parameters of the model, and then it's just a matter of a choice of an optimization algorithm in order to find a low enough minimum point of this loss function. And that's it. So once we found a good configuration of parameters and we minimized this loss function, we end up with a huge dynamical system, nonlinear dynamical system, with all these finely tuned parameters, which somehow provides a good output in response to the input provided to the network. And this will solve the task. So what's the problem? The problem is that we usually have no clue on how the recurrent neural network is effectively behaving and how the neural network made some choices. And that's a problem, because we don't want to just rely and trust these neural networks. We might want to understand how they behave. So the question is it possible to provide a mechanistic model of the functioning of a trained recurrent neural network? And so that we tried to answer this question in this paper here, published in Cognitive Computation, where we exploited these attractors called excitable network attractors in order to open the black box of recurrent neural network. And I'm going to briefly explain and summarize what we found in the idea of this paper in Cognitive Computation. So what is an excitable network attractor? An excitable network attractor is a global attractor that looks like a graph where nodes are local attractors, and the edges of the graph are the excitable connections between those local attractors. So let's imagine to zoom into this area of the excitable network attractor, and what we can find in phase space in a real application might be something like this in the right picture. So here in this particular case, all the local attractors are stable points, and if, for example, the internal state of the network is in a neighborhood of the stable point C0, as you can see, there is an unstable point close to this stable point. The dashed line is supposed to be the stable manifold of the unstable point here, and through some input perturbations or some noise, the internal state of the network might eventually cross this manifold and so starting to converge towards another local attractor, which is C1, the stable point C1. And once here in a neighborhood of C1, again, by means of some input pulse or noise perturbations, we can cross those manifolds here close to the stable point C1 and switch towards another attractor, another stable point, in this case C3 or C2. And those are called the excitable connections between local attractors. So the main idea of this paper was to extract an excitable network attractor observing a trajectory of a recurrent neural network while this was running. And so those are the two main steps of the procedure. We provide as input a trajectory of a recurrent neural network while it is solving a task. So first we detect the attractors of the system, and then we find the excitable connections between them. And also we try to estimate the excitability thresholds of those excitable connections. So at the end we end up with a weighted graph representing the effective excitable network attractor, which encodes the underlying dynamics of this particular recurrent neural network. And we showed that excitable network attractors can explain the functioning of recurrent neural networks in some tasks that require switching between attractors. It is useful to assess robustness to noise thanks to those excitability thresholds, and also this model can be exploited to provide a mechanistic interpretation of the errors occurring during the computation. And I want to show you an example of that. We found this task in this paper of Suzziller and Barak, which is called the flip-flop task. The task has in this particular case with 3 bits, has 3 inputs and correspondingly 3 outputs. So let's focus on the first component of the input here. As you can see, is almost everywhere 0, but sometimes we get some pulses of +1 or -1, as you can see. The task is the following: if the input is 0, the output of the corresponding component must remain still. once we get a positive pulse, then the output of the first component must switch from -1 to +1. And then when we get a negative pulse, the output of the first component must switch to -1, and so on. Moreover, if the component of the output is already positive and we get a positive pulse, the network must learn to do not move, as you can see here, until we get a negative pulse, and so the second component of the output must switch down to -1. And here, as you can see, we get another negative pulse, but we already are in the -1 value, so the output must remain still. And we trained a recurrent neural network in order to solve the flip-flop task with 2 bits. As you can see in this plot, the black trajectory is the target output and the red trajectory is the generated output of the network, and we can barely see the target output, which means that this neural network has learned quite well to solve the task. Apart from some slight differences, for example around here, as you can see, where the generated output differs from the target output. Now, if we use a mean square error as index to evaluate the quality of this recurrent neural network, we will find a very low value, and that's because almost everywhere the neural network produces a very good output compared to the target output. But we don't know what is actually happening around here. We don't have an interpretation of this particular error that we are observing. But if we extract the excitable network attractor underlying this particular recurrent neural network, we see that this particular neural network has developed 6 local attractors instead of 4, which will be the optimal number of local attractors, right? Because there can be just 4 outputs combinations, which are respectively -1, -1, -1, +1, +1, +1, and +1, -1. As you can see here, the network developed 2 spurious attractors, and what's happening here is that this excitable connection between the local attractor corresponding to the output values -1, -1 is switching to the local attractor through one of the spurious attractor, which has a output values which are not -1, -1, but are slightly different, which are this value here and this value here. And so this excitable connection has been activated because it is quite low, this number, which represents the excitability threshold, and that's what happened here. And that's very cool because it allows us to have a mechanistic interpretation of what's happening here, which it wouldn't have been possible with for example, the mean square error. And that's cool. Alright, so what's the problem with this procedure is that we cannot use these tools of the excitable network attractors for general tasks, and that's because they rely on autonomous dynamical systems theory. We can force these arguments to impulsive inputs or piecewise constant inputs, but we cannot use these for generic time-varying input signals. But we want to go further and deal with recurrent neural networks driven by any kind of input signals. So this requires to switch framework and use tools from the non-autonomous dynamical systems theory. And I suggest you, for whoever wants to approach non-autonomous dynamical systems, this book of Clausen and Rasmussen. So starting this journey on non-autonomous dynamical systems, I think a good starting point would be the acoustic property. The acoustic property, I was fascinated about this concept when I first approached reservoir computing, because it seems that apparently this acoustic property, it is a property that recurrent neural networks must possess in order to function correctly. Here you can see a snapshot of the original definition of Jaeger of the acoustic property. It says that a network has the acoustic property if the internal state at time n, xn, is uniquely determined by any left infinite input sequence. So that is basically a request on the structure of the pullback attractor of the system. This implies that given an input, the recurrent neural network will produce a unique response, and it will forget any internal states and end up following a unique, possibly complex attracting trajectory, which I depicted here as the black trajectory. Of course, this is a discrete time trajectory, and if we start the system with two different initial conditions at the same time, which are represented here by the two squares, the blue one and the red one, the system will start to converge downwards towards this black trajectory, and the red and the blue trajectory will get close to each other more and more, and to the black trajectory as time flows. It's interesting, it's key in an autonomous system to consider the initial time. For example, if we start the system from the red point, the system won't follow this branch of the black trajectory, even though it's really close to this black trajectory, but rather will go down to the black trajectory, and after a while it will follow this branch of the black trajectory. And as a matter of fact, when we start the initial condition here, this branch of the trajectory doesn't exist yet. The acoustic property is obviously a request on the reliability of the system. We want one trajectory, and we want, regardless of the initial condition, follow this particular trajectory. But it seems to be too much restrictive to my eyes, and that's why we developed a generalization of the acoustic property, which allows us to consider many reliable responses for a particular input signal. So that the main idea is to define an echo index for the system driven by a given input sequence U, and this number will quantify the degree of non-autonomous multistability under the action of that particular driving input. Here I want to show you an example that we found in this paper that you can find in the references and the bottom of these slides. A paper by Hoerzer-Legenstein-Maass, where the neural network here must develop two, let's say, attracting trajectories in order to solve the task. The task is the following. The inputs provided to the network are two input signals, the red one that you can see here and the green one. As you can see, those are quite random, time-varying input signals. And there are also some input pulses provided to the network. The network must learn to reproduce the green signal or the red signal according to the context, which is given by an internal memory, which can be on or off, on for the value of +1 and off for the value of -1. And this internal memory is driven by those input pulses, as I said before. So there are two outputs. The first output represents the internal memory of the neural network, and it is represented as the black trajectory here, which is just behind the orange trajectory, which is the target output of the first component. And the second signal in output is the black trajectory that you can see here, which is, as you can see, following the red signal as long as the value of the internal of the first output is +1. And when the internal memory switch to -1, then the second component of the output switches to reproduce from the reproduction of the green signal to the red signal, as you can see. And then around here we switch towards the value of +1, and so the network will switch and start to reproduce again the green signal. So that's the task, and we thought that in this particular example there might be two attracting trajectories. So what we did is to turn off the pulses, the input pulses driving the internal memory, and run many initial conditions. And that's what we got. As you can see, there are initial conditions that converge to the output value of the first component of +1 and other to the value of -1. And correspondingly, in the second component, some initial conditions will lead to converge to the non-autonomous attractor corresponding to the green signal, and others will converge to the non-autonomous attractor corresponding to the red signal. And we thought to investigate also in phase space this non-autonomous attractor, and that's how they look like in the first two principal components, and they look very messy, but nonetheless they are indeed very, very stable. As you can see, running many initial conditions, all these initial conditions converge either to the red attractor or the green attractor. So we want to we devised a mathematical definition suitable for describing these kinds of non-autonomous attractor. And we ended up to this definition that I won't actually show you in detail because I don't think it worth in terms of time, but I will explain the idea of what we call uniformly attracting entire solution. Basically, we consider those trajectories defined in the forward in time and also backward in time, which are usually called entire solutions, and I will call from now on these trajectories, which are left infinite and right infinite, entire solutions. We consider those entire solutions which uniformly attract in space and time portions of phase space with positive Lebesgue measure. Informally, we can see these uniformly attracting entire solutions as good non-autonomous fixed point. And we also provided in this paper, published in Physica D, a kind of input-driven fixed point theorem for detecting uniformly attracting entire solutions. The basic ingredients of this theorem are a compact subset Q, which is positively invariant. Positively invariant with regard to this universe of input sequences. Being positively invariant means that if we get inside this compact subset, we won't get outside of it. So we get trapped inside this set. That's what roughly means being positively invariant. And if this compact set is such that the first derivative in space of the map G, which is the map describing the state update rule of the recurrent neural network, if the supremum of this norm is less or equal of a value mu, which is a constant real number between 0 and 1, and assuming further that this space is also convex, then we can state that for all input sequences in this universe of input sequences, we'll have admit a unique entire solution inside this compact space. And such entire solution is a uniformly attracting entire solution. And now I want to provide a simple two-dimensional example of application of this input-driven fixed point theorem. And here there is the equation of a recurrent neural network without leakage. We've got as activation function the hyperbolic tangent. The reservoir is this diagonal matrix here, and this matrix is just the identity matrix, so you can forget about it. We are just adding the input vector here. Input can assume values, just two possible values, the vector A, which is this one, or the vector B, which is basically minus the vector A. So these are the two only possible choices for the input. This non-autonomous dynamical system is equivalent to a switching dynamics between the two autonomous map, one that we can call FA, which is the one obtained using a constant input vector A to drive the dynamics, and the other that we can call FB, which is the one obtained using just vectors of value B at all times. And it turns out that the autonomous map FA has two stable nodes in blue here, and a saddle and unstable point in between them, disposed along this vertical line here. And analogously, the map FB has got two stable nodes and an unstable one in between them along this vertical line on the left. And I put all together in the same plot these attractors in order to view the non-autonomous dynamics of this simple system. So I generated a input sequence of values A and B with randomly with equal probability to pick up the value A or B, and I used this input sequence to drive the dynamics of this system. And if we start, for example, with this initial condition, the system will start to converge towards this stable node here, and then after a while the B value occurs, and so the system switch rule, and so it will start to converge towards this other stable node, and so on. It goes upwards, zigzagging like that, and it seems to converge here to something, and this something is a uniformly attracting entire solution. And we can prove with the input-driven fixed point theorem that these convex and compact subset of phase space, which I'm drawing with my mouse, this rectangle, is in this rectangle the hypothesis of the theorem hold. In this particular case, it's easy to analytically compute the first derivative of this map, and we've got everything, and so we can prove that inside this rectangle there is a unique entire solution which is uniformly attracting. And the same can be applied in this region, this rectangular region here, and so we get that inside here there is another uniformly attracting entire solution. And also this holds for every input sequence of values A and B. And then in the bottom plot I plotted the arithmetic average of the two variables x1 and x2 of the system for many initial conditions, and as you can see, all of them converge either to the upper uniformly attracting entire solution or the bottom uniformly attracting entire solution. So we can say that in this particular example the echo index is 2. So that's the idea, and in this paper we rigorously provide a definition for the echo index, which I'm not showing here again, but I'm just explaining roughly what it means. We say that the system driven by an input sequence U has echo index n if there exists a number n of uniformly attracting entire solutions such that they attract the whole phase space except for a zero Lebesgue measure set. So I think that this picture is quite self-explaining. The black trajectories are the uniformly attracting entire solutions, and the blue arrows describe the vector field of this dynamical system, which suggests the convergence towards the black trajectories. And apart, but as you can see, there might be some entire solutions like this, like the red one, which are defining the boundary between the two basins of attraction of the uniformly attracting entire solutions. And these kind of solutions exist, and and are also attractive, but the basin, let's say, of attraction of these particular solutions has a zero Lebesgue measure set, right? So we can get rid of these, and apart from this particular solution, all the other initial conditions will converge towards one of these two attracting trajectories. So that's why we need to exclude some zero Lebesgue measure set. Another application of the input-driven fixed point theorem is that we were able to prove, always in this paper here, that recurrent neural networks driven by very large in amplitude inputs have always echo index 1. So using large amplitude inputs will induce recurrent neural network with the echo state property, right? With just one attracting trajectories for all initial conditions. And the hypotheses are those that I just mentioned at the beginning of this presentation. And yeah, that's the theorem. I won't talk about all the details. You can check this paper, exactly this theorem is proposition 4.6. What this result implies is that the subset of all input sequences having echo index 1 is dense in the space of all bounded input sequences equipped with the product topology. That is the topology induced by, for example, this metric here. And that's because the product topology allows arbitrarily large variations of the input in the far past or far future. That's because as you can see, this average, it's weighted with the power of 2, which is depending on the time k. So two extremely different input signals in the past will be very close to each other in this topology induced by this metric. While the uniform topology seems to be more suitable for the stability analysis of many reliable responses over recurrent neural network, right? For example, if we include noise in our model. That's the uniform metric which induces the uniform topology. As you can see, we check for the maximum difference between two input signals at all times k. As last result, I want to talk about the existence of echo index n for small amplitude input perturbations. So what we proved is that if we have a autonomous map f having a fixed point x star, a fixed point such that it satisfies this relation, which means that it contracts a neighborhood of itself of radius delta with a ratio of m, where m is a constant, a real value between 0 and 1, if an autonomous map has this particular stable point that we call uniformly attracting stable point, then slightly perturbing this autonomous map with an external input, we will get a non-autonomous dynamical system such that it has a unique, uniformly attracting entire solution confined in a neighborhood of the position of the point of x star, which was the stable point of the autonomous map. So that gives us a way to see how those uniformly attracting entire solutions can be generated. For example, they can be generated from an autonomous map and perturbing with some noise or small input perturbations an autonomous map. And what we observe, the corresponding non-autonomous attractor will be, in that particular case, a uniformly attracting entire solution. That also implies that if we slightly perturb an autonomous system possessing a number n of those stable points, will lead to a non-autonomous system where a number n of uniformly attracting entire solutions coexist. So with echo index n. And also that the echo state property cannot hold for in general for small amplitude input signal unless we put some restrictions on the reservoir. Yeah, finally, I pinned here some possible and interesting research directions. First would be cool to exploit this generalized echo state property in more realistic and useful tasks in machine learning, like classification tasks, counting problems, or generally for diagnostic of errors. Another interesting direction would be to extend the excitable network attractor setting to the time dependent to the general time varying input signal setting, right? So devising a non-autonomous excitable network attractors where instead of stable points we consider uniformly attracting entire solutions, and we model the excitable connections, the non-autonomous excitable connections between those uniformly attracting entire solutions. And finally, it would be cool to look at the result on how different training mechanisms affect the properties of those attractors of these recurrent neural networks. And that's all. Thank you for your attention. I will maintain for a few seconds the references for you. And that's it. Thank you.